Hello everyone. So in this session we'll just deal with the uh, thermal analysis by using flow simulation. Let's consider the scenario. This is the heat sink at the top, and this is the chip and the insulator we have. And this particular chip gonna produce on an average of 150 watt heat. So with respect to that, how the heat sink gonna just deal with this, we need to cross check. And even I need to flow an air to just to maintain the cooling inside the circuit board we can consider here. So in short, we're gonna deal with thermal analysis with airflow. Okay, let's deal with the same thing now. I'm gonna just switch to the thermal analysis. So by using wizard, I'm gonna create a study that is cooling, and I'll just name it as thermal analysis. Okay, so in the unit system you can just change the units as per your requirements. So here I don't want the temperature should be in Kelvin, I'll change to degree Celsius. And here I'm gonna consider the external for not the internal. Fine, so the heat conduction solid should be activated as we are dealing with this heat sinks and all. If you want, you can activate the gravity. Okay, gravity should not be along C, it should be along Y for me. Here it should be 0. Okay, you could able to see the gravity direction downwards. Okay, well, so here the gas is ideal air. I'll just add the same, and here I need to define this solids. So here I'm gonna consider the insulators. So from the classes and the minerals, I'll just choose the insulator. Okay, so by default it is insulator. If you are going to define the metals or materials, according to that they will change. We'll see that one later. And now here the roughness I'll keep as default. I'm not going to change anything here. Finally, room temperature I'll just specify it as 25 here, and if you want you can just define the solid parameters. Initial solid temperature as 23, that's okay for me. The velocity along z direction, could see, just define with respect to z direction 90 minus 15 meter per second. Okay, 15 or 20, it's okay for me. 20 meter per second I'll take into account, and I'll just finish the shutdown. So according to that, the computational fluid domain will be created. You can use your screen to orient, and you can adjust it. Otherwise you can utilize the manual method. Just you can go inside the computational domain settings and you can change it with respect to your values, but for me I think this is fine. Approximately I'm gonna just deal with this. Okay, so once you define your fluid domain, you can simply hide it for your convenience. And then as we have already defined the airflow 15 to 20 meter per second, we don't need to worry about it. I just need to define the solid materials. So I'm gonna add the solids. So from the predefined materials, the chips should be made of silicon. So I'll search for that. Okay, let me just define the alloys. Copper I need, so the copper here. Metals, and the copper here. So I'll define copper for this, not for this. Okay, and I need to define the material for this also. And go ahead and you can add it. Solids. From there I need the silicon now. And select it. Okay. So now the insulator by default will be selected for this. You don't need to worry about it. Otherwise, if you want to define it, you can just define the same. So I'm gonna just keep it as it is, not to worry about it. Now I need to define the heat source. I can just select the conditions. From there you can define the volume heat source. You can just select the chip. You can define it as 80 or 150 watt as per your requirements. Okay, and then meshing, very important. So you can utilize the global mesh and define it manually. Otherwise, if you want to utilize the advanced method, you can activate this advanced method. You can directly go to manual, or you can directly use the settings here if you want to deal with. But I'm not gonna consider that one. That will take much time to just deal with these all the steps. So we have the one more option, that is insert local mesh. We have the regions. You can select it. According to that, you can set the regions. So I'm just gonna consider only this much regions into account. Okay, only this region should be meshed, and you can use the refinement here. Okay, and if you want, you can set the values, advanced refinements, curvature criterions and all. Okay, you can directly click on green check. So once you're done with that, finally you just need to run the study to get the results. So I'll just switch to the results tab, so you can just have the quick overview of the results and just load the results. If you have run the study before, you can load it by using load and unload option. So the first thing is this. You're able to see this one. So if you want, you can hide the components for now to see how exactly the temperature is changing. So here I have taken 150 watt into account. I think it's 130 watt. Okay, according to that, this is how it is varying inside. And then we have the isosurface plot. This you could see here. If you want to animate it, you can use the animation tab. Okay, there is no changes into this. Sorry, this cannot record the animation. Sorry for that. I think for that we don't have animation, so here it is. Okay, this is how it is distributing on the heatsink. Okay, and then we have the flow trajectories. If you want, you can activate that even. Okay, so from here I am flowing the air, and I'll just simply hide these for now. Let me just even hide this. So if you want the components back, you can bring them back. Then you can even play the animation for this. You're able to see the air is taking away the certain temperature level, and you could see at this region also. So if you want to have a more clear visualization over there, you can just Consider the error size lesser. Can increase them. See these regions, right? Could able to see. Okay, so this is how you need to deal with thermal analysis by using flow simulation, that is kind of cooling. Thank you, stay tuned.